In this course of nanocomposite, we will be talking about silicon carbide. It's a very important material and is used in many nanocomposites, and it can be considered to be a high performance material, and the reason is that it can withstand abrasion, high temperature, high pressure, and I should say severe unfavorable atmosphere. And considering its application, it finds application in so it's called as some of the main applications of silicon nitride are finds high application in heat engines where high temperature is required. Then finds application in nuclear fusion reactor. Then chemical processing industry. And aerospace. So these are the few areas where silicon carbide is widely used. Now, in order to meet these demands, it requires introduction of expensive and rare metallic alloys, right? Now, normally, so which actually requires a very completing cooling arrangements. Okay. Therefore, that means if instead of using silicon carbide, now these applications will require such alloys which need some additional cooling arrangements. Now that is where the silicon carbide is useful, because no such additional cooling arrangements is required when you are using a silicon carbide. Now, apart from that, silicon carbide has the potential to satisfy requirements of most of the applications, and it is also called a high temperature structural material. So let's call it silicon carbide is a high temperature structural material. And to be specific, it has good oxidation resistance, it has good creep resistance, it has high hardness, good mechanical strength, that means high UTS, and high Young's modulus, so that comes under good mechanical strength. It has got corrosion resistance, corrosion as well as erosion resistance. Erosion is where material loss actually is taking place. Corrosion is where an oxide layer is formed on the top and material decay takes place. And the most important thing, it has a relatively low weight, so that makes it more attractive. This low weight compared to the alloys that we can use. And apart from these, the raw materials that are required to make silicon carbide are inexpensive. So I should put it inexpensive precursors, and it can be actually molded into different shapes. So there is no limitation in different complex shapes that can be used. Now we would first start with application of silicon carbide in something called ceramic engines. Now, the application of silicon carbide in ceramic engines offers a high efficiency of the engine, and which could be operated at a high operating temperature, and therefore in complete combustion of the fuel actually takes place. So complete fuel consumption. Moreover, the material has only 1/3 of the density of superalloys. So, being a lower density, that means that is it's almost 1/3 of superalloys. So that makes it even more acceptable material. Now, silicon carbide, if we consider a ceramic engine, there are many areas where the silicon carbide can be used. For example, it can be used in turbo rotor. It can be used in piston liner. All from mechanical background can very well know what these are. And it can be also used in valves. Apart from these ceramic engine, there are other applications of silicon carbide, like in turbine wheel combustion chamber. And also in rotors of various dimensions. Dimension is not a problem, as we have already explained. And also used in nose cones. Now, the properties of inherent hardness, chemical inertness, and abrasion resistance. It makes silicon carbide applicable in chemical processing industry. So, in chemical processing industry, silicon carbide finds application as in seals and valves, nozzle for sandblast, in lens mounts, and wear plates for spray drying and wear dyes. Okay. Now, the other applications of these wear and erosion resistant silicon applied. So, we consider wear and erosion resistance as the specific properties of silicon carbide. Then, based upon these, it has got specific application. Like in aircraft, journal bearing, thrust bearing, ball bearing, oil patch plunger, pump impellers, pump components, other pump components, fixtures, mold billets, and extrusion dies. Now, apart from this, if we consider the thermal shock resistance and keep resistance, of silicon carbide, then these are the following applications as heat exchanger tubes, as diffusion furnace components. And as furnace rollers. Okay. Now, when we talk about ultra fine silicon carbide, because these ultra fine, which are actually synthesized in the form of powders, have physical and chemical properties which are in fact superior, even superior to the normal silicon carbides. And it's basically the emphasis is mainly given on the preparation of ultrafine ceramic powders, and it is basically done with the help of sintering and having high density and lower sintering temperature. So we mainly use sintering to make these silicon carbide, and we mainly focus on the final product to be of high density and lower sintering temperature. Now, so we next move to the nanocrystalline regime. Now, in nanocrystalline regime, the nanoparticles have a tendency to agglomerate. So, agglomeration is a big problem. So, when you go to nano, then agglomeration is a big problem. So, now when there is an agglomeration, then a decrease in storing stress energy. So there is an agglomeration that is taking place. So it results into the stored stress energy it actually goes down due to the agglomeration, and due to this and increased stress for initiating fracture and generation of nanoparticles may take place. Now, there are two principal factors which need to be controlled to obtain nanoparticles. First of all, so two factors to prevent this agglomeration. First of all, the ratio of the weight of the metallic balls. Suppose you are using a ball milling, so weight of the metallic balls of the grinding media to the weight of the particles to be processed by the grinding route. So weight of metallic balls divided by the weight of the particles, which, or I should say, weight of the precursors, which have to be grinded. Because in grinding, we consider grinding as one of the options to make silicon carbide. And the other thing is that the grinding media should actually be semi-fluid viscous. So semi-fluid or viscous nature of the grinding media. These are the two factors which needs to be taken care of if we would like to prevent this agglomeration to be taking place. Now, another factor which is important in the time of grinding, which also needs to be controlled in order to optimize the process of grinding particles, is the time of grinding. Total time of grinding dates also needs to be controlled. Also, the purity of the precursor is also important, of the material that is being used. Now, commercially, the silicon carbide is available as alpha silicon carbide, and which is actually made by a process called Acquisition process. Where a mixture of sand and crushed coke, sand, crushed coke, with common salt and sawdust. The mixture is made of these materials, and these are then electrically heated. This mixture is electrically heated at a temperature of about 26 degree C. Now, the reaction, if you consider the reaction, it is basically SiO2 from sand plus carbon giving rise to silicon carbide and emission of carbon monoxide, and this is basically a reduction reaction, and it actually results into silicon carbide grains. So reduction of silica actually takes place, and it leads to silicon carbide grains. Now, the reason of adding the sawdust here in this reaction is to increase the porosity of the furnace charge, and so sawdust is used to increase porosity and by increasing the porosity, the circulation of the gases of the reaction gases is much more efficient, and it actually also helps in removal of carbon monoxide.